Rethinking, second edition, chapter 15, and we're on question 15H4. And this is a big, long question, so the answer starts here. So all of this is question. And so I'll kind of let you read it for yourself, but essentially what's going on is we're going to the primates 301 data set, which I think we've used a couple of times, and we're trying to establish the nature of the relationship between brain volume and body mass. Okay. So the first thing we do is load that data. Now the next thing that we do is to add some error to the measurements. Okay, so we're dealing with measurement error here, and we're trying to see how that maybe changes the inference, after adding measurement error. So here's our data, and then we add error. So here's the standard error for, I guess, brain volume, and then for body mass. And notice that they are proportional to, the original brain measurement and body mass measurement, right? So it's 10% of whatever those are for each species. Okay, so again, so in the primates data set, there's a bunch of measurements on a bunch of different primates, everything from itty-bitty things to gorillas or something, so there's a big span of sizes for these animals. Okay, and so we model these things as such. Okay, so we're measuring brain volume as a log normal distribution that is a function of body mass. Okay, yeah, so this just kind of gives you some more details on the model, but in the end, it gives us this model to run, and so we run this model, and we'll look at the summary output here in just a little bit. Okay. What we do is to add in the measurement error, right? So this model is ran without measurement error. We're going to add in the measurement error and then compare the two models. Okay. So here's the new model, right? So here's the new data set with the standard errors given. It suggests that we use a start list and some other things. I think that it also suggests that we adjust the max tree depth here. Okay. So I go through and I notice some things in the code here that are a little bit tricky. Again, one thing is that when you're trying to find things like measurement error or imputing values, the order in which you're putting in these parameters matters. Okay, so I don't know if it does directly in Stan, but as Ulam is passing these things to Stan, they have to be in the right order. So there's that. And the other thing is I've noticed this here recently. I think maybe Stan has updated and Ulam has not. But some of these arguments, like this control data list here, it doesn't work for one thing, which is unfortunate. So you can set the max tree depth to whatever. I think 15 is the highest you can set it, and the default is 10. But it doesn't seem to do anything once it's in Stan. It just becomes a null argument. The other thing that I noticed here was that you actually had to have both of these arguments in the control in order to get the thing to run. Otherwise, you get errors. And then similarly, in the start, right? So if we're giving Ulam, or if we're giving Stan some starting values to begin its algorithm to find estimates for these guys, you actually have to give starting values for each parameter. So again, I think that's just the way that maybe Stan has updated and Ulam has not. Okay. So anyway, so we run both of these models, and then we'll just look at the Preci outputs here, and we see that they're basically identical. Okay, so this is the top one here is the measurement error model, and the bottom one is the no measurement error model. And you notice that the estimates, at least for alpha and beta here, are identical. Maybe with some small differences, but they're basically identical. If there is a difference, it's in the sigma parameter. Maybe sigma is a little bit bigger in the measurement error problem, but that could also just be sampling variability. But whatever. So that's interesting. But the question is why, after adding measurement error, why are the inferences so similar or identical, maybe even? So the first thing that comes to mind is I'm not actually sure why we might expect measurement error to drastically change the inferences, right? Because we have the signal in there, and the noise is it's just noise. And so as long as the model can pick up on the signal, the signal should be the same in both cases. So I'm not actually sure why we might expect that to be the case, but um, um, so I expect that the mean values would be very similar, but I might expect that the standard deviation or the credibility intervals to get bigger as we added measurement error. And that doesn't seem to have happened here, although again sigma may be a little bit bigger. Um, and so if that is the case, then then apparently in this case maybe we didn't add enough error for that to be the case, and it kind of makes sense that that would be the case, or possibly. Um, so remember that when we added standard error, we did it in proportion, to the size of the animals. And so when we go through and so now I trying to follow up on that. I made a histogram of brain sizes and body masses, and notice that most of the animals are very, very tiny. There's only a few big animals. So in other words, most of the standard errors that we add are very, very tiny, right? Um, so the overall amount of error that we've added is very, very tiny, which suggests that the model did not have to sift through an excessive amount of noise in the first place, right? It was, uh, we didn't add much, we didn't add a lot of noise anyway. So, okay, call that good.